Okay. So yeah. Um, well, you guys just took your exam. I guess I should ask, how did it go? Do you have any questions from that? We can go through
I
that a
have
little
a
bit.
question actually.
Okay, yeah.
So because of the incident thing that happened, will that push back our getting our tests back, or will they be still graded and returned to us around whenever they were supposed to?
Yeah, I don't think that's going to change the when we need to finish grading. So for us, we're supposed to have things done by Thursday. That might get pushed back a little bit depending on the other grading teams, but we're aiming to have all the grading done by Thursday, and then, well, you should be able to see your results by then.
So by the end of this week, we should know what we got.
Oh yeah, yeah.
Okay, cool. Thanks.
Hmm.
My part two actually has already been annotated and been given a score. So you might want to check. It won't have a grade in your grade book, but if you go and click on your submission, so I think Craig Spencer did it, and he made notes about what you did right and wrong.
Okay, so you guys can see your grades live in a sense. It's convenient. Yeah. Okay. Well, I mean, if you want to, I can go through those questions, but I already recorded videos for them. I'll make those public once the grading is fully complete, and then you guys can I guess see how the calculation should go. And also Spencer will probably email out a full solution thing to the exam.
When
Again,
you're talking about that, is that in the comments, or how do I see if he?
oh, the comment. Oh, comments to when he writes.
Yeah, when he was talking about he could see the annotated grade or whatever.
So when you open it up on, I think it's SpeedGrader or whatever, like the thing on Canvas, when you open it up, if the grader writes an annotation, it should be like a pin that then expands out to a box that is like the whatever the person wrote. It's like in a comment. I think you can even put math in the comment because it'll render LaTeX. So it depends on just how much the grader wants to actually say, but you should be able to see. Okay. Other questions? If not, we will get started with number 6. I should copy that in. Just a sec. Yeah. So, and I should also say, if it ever seems like I'm going too fast for you, just tell me to slow down. I'll try to slow down. Or if you ever need me to repeat an explanation, I can do that as well. Although, I mean, since everything's being recorded, you can always just play it back. But yeah, so I think that for today, we'll probably be able to get through to problem number 4. And then we'll just, Thursday will be a bit of a shorter thing, but we'll just finish the last 3 problems on Thursday. Okay, so, and I'm sharing just am I sharing my full screen or am I sharing OneNote? Just OneNote, I think. Okay, yeah, so I believe that you talked about 2 things this week. You talked about implicit differentiation, and you also talked about related rates. So, well, first we've got, what is it? 2 problems, but 1 problem with 2 parts, 1 problem with 4 parts. That these 2 problems, they go over just how do you do implicit differentiation. And so the overall idea for implicit differentiation is that, let's see here, how do I scroll over? Okay, there we go. Implicit differentiation. The idea is that if you encounter an x, you differentiate like usual. But if you encounter a y, you need to do something different with it. You need to treat y as though it's a function of x. And so when you take the derivative of y, it doesn't become 1, it becomes this symbol y prime. And usually you see that people use the symbol dy dx. but that uses more handwriting, and so I tried to not write dy dx. I write y prime, where I implicitly know that my prime here means I'm taking the derivative with respect to x. Okay. And so just, I guess, as another example, if you have y to, let's go fully general, y to the nth power. So power rule would normally say that this would be n times y to the n minus 1 power. But you have a chain rule, sort of, where that says you have to take the derivative of y. And y is this fancy thing that has a y prime attached to it. Again, we sort of are thinking of y as a function of x. And so there's this y prime that lingers around. It's all because these derivatives that we're doing are supposed to be with respect to some other variable that isn't y. So like in these problems 1 and 2, the normal derivative is with respect to x. But then when we get to related rates, our normal derivative is actually with respect to t for time. And so that's why implicit differentiation is actually related to the topic of related rates. All right. And we'll encounter related rates when we get there. So yeah, let's now just go ahead and do part A. So we want to take the derivative of this equation. Find y prime, which is this, is what it's saying. And we just want to take the derivative. So if we go ahead and calculate this, well, left-hand side, I have to use product rule. So I will get a 2y cubed plus x squared times 3y squared y prime. Okay, so did you guys follow that?
Could you repeat it again?
Okay, so this is product rule, right? Taking the derivative of the left-hand side. You see that as product rule because it's a product of two things. It's product of x squared and it's a product of y cubed. So what I'm doing is this part here, this is the first half of product rule where I take the derivative of the x squared and then I tack on the times y cubed. This is the other half of product rule where I take the derivative of the y cubed part. And notice that the y cubed, we have that 3y squared times y prime. So this is where the implicit differentiation starts taking hold because we were taking the derivative of something that wasn't a function of x, or well, that isn't written in terms of x, but it's instead written in terms of y. Okay. And now we want to do the right-hand side. So we want to take the derivative of this whole thing. Well, so we have a power out here, which means that the first thing we should do is take a power rule, or do the power rule. So we'll have a 3 and then contents inside. And then we decrease the power by 1. So all I did just now was I applied power rule. But because the inner function is complicated, we have a chain rule. So we need to take the derivative of the inner function. So we go ahead and do that. Derivative of the x squared is just 2x. Derivative of the y squared, now we need to use the new rule that we've learned. So 2y would be what we normally would write if this was a derivative with respect to y, but it's not. Instead, we need to put a y prime because our derivative is with respect to x here. And then derivative of -1, well, that's just 0. So we can close our parentheses. And there we go. So that was taking the derivative of the full equation. Okay. Now, well, I guess I'll pause and I'll ask, are there any questions? Does this make sense to everybody? You can I don't know. How do we make it so people don't like speak over each other? Any questions? Does that make sense?
Yes.
Yeah. All right. Great. Great. Okay. So right now, what are we trying to do in this problem? We're trying to find y prime, which is also written as dy dx. We're trying to find this quantity. Well, we have a y prime here, and we have a y prime here. You can see, well, maybe it's easier if I use my cursor. You can see y prime here, and you can see y prime here. You can see it in two places. what we need to do is we need to solve for y prime. So now all that's left is we do algebra in order to bring y prime to one side and everything else is on the other side. So the way I'm going to do this is I'm going to see, I want to not write so much, especially because, you know, this is on a computer. So I want to cluster all of my terms that have y prime on the left-hand side, and I'm going to bring all of my terms that don't have a y prime to the right-hand side. So notice that we have this term with a y prime. We've got this part, okay? So you're going to have to visualize that I'm distributing this 3 quantity squared to both of these terms. So I end up separating that out into 2 different terms. And then one of them has a y prime in it. One of them does not have a y prime in it. So I bring the term with the y prime to the right-hand side, and there'll be a minus that shows up as a result of that. Okay. And I'm going to factor out automatically. So I'm doing a few steps mentally. And so we'll get this from this first term in green. And the second term in green is going to contribute something that's negative because we subtracted over. So I multiply this and that, I get a 6, and I'm going to get a y x squared plus y squared minus 1 squared. This is the left-hand side, okay? And now the right-hand side, well, we have, maybe I'll use blue, okay, fine. So there's this term with the 2x and this stuff that distributes. There's also this term. So I will need to subtract this first blue term over to bring it to the right-hand side. And well, normally we would like to write things without a minus in front. So I'm going to write 6x and then this quantity squared. And then we subtract off this first term in blue. So that's a 2xy cubed. Okay. So any questions on this algebra? Made sense? Everyone's following along? Okay.
Actually, why did you like the 2xy cubed, like the one you underlined in blue? Why did you have to move to the other side of the equation?
Well, because I want all the terms with the y prime on one side and all the terms without the y prime on the other. Because the last step I'm going to do, see how I've got this y prime, I factored it out. I factored it out of these 2 terms that both had a y prime. The last step I'm going to do is I'm going to solve for y prime by just dividing this big thing in parentheses over. And then that, as a result of that, I'll have y prime equals, and then just this formula that is a big fraction.
Okay, that makes sense. I remember doing that.
Yeah. So like what you're saying is kind of like if I just left the 2xy cubed, the next step that you would do is you would subtract it over, because then you divide. So it's the whole process of solving for y prime, but I'm condensing it into 2 lines of work rather than, I don't know, distributing would be like 1 line, moving things would be another line, dividing 3 lines, I guess. Or yeah, you could make it like a lot of lines of work, but you only need 2 lines of work. Okay. So now I divide over. Okay, and what do we get? We get 6x squared plus y squared minus 1 squared minus 2x. I'm just copying down the right-hand side right now. And then now I divide over. And now I just copy down the stuff in parentheses. There we go. And so that's my answer. And I can box that, I guess. All right. So that was part A. And now part B. So part B is really just asking us to use what we found in part A. So it's saying find the equation of the tangent line to this. Well, the process of finding the tangent line requires that we find the slope and then also a point on the line, right? We use the point slope form. Well, once we have this derivative, if we evaluate it at this point, and in fact, like maybe one thing you should check is that this point does lie on this curve. this is some curve. You can graph it in Desmos if you want to. You can just like type this out explicitly, and then like, I mean, just like as it is, you just type it out, it will graph something. And then the idea is you want the tangent line to be tangent at this point. So the idea of this, you should really think of this as a function that takes in two inputs, an x and a y. So we can kind of, in fact, I might as well just, start thinking about things in a sort of a multivariable kind of way. If you plug in the x coordinate and the y coordinate, you're going to get some number. And that number is actually the slope of a tangent line. Okay, so we go ahead and do that now. And symbolically, we would use a vertical arrow for like a meaning, what is it, evaluation. So I'm saying I'm evaluating at the point 1, 1. Okay, and now it's just arithmetic. Let's see. 6 times 1, 2 minus 1 is 1. So that's that minus 2 over. It's very convenient that it's 1, 1. Otherwise, there'd be a lot more numbers I'd have to write down. 6 times 1, and this is also 1, right? Yeah, okay. So 4 divided by -3. All right, so we found our slope. Okay, are we done? Answer is no, right? This is I think I know that like some people, they would stop here, and then they've only done half of the problem. We found the slope, right? But we're looking for an equation of the tangent line. Find the equation of the tangent line. All we found so far is the slope. We need also to use the point, and we take the slope, take the point, put it together. The process that you should be comfortable with by now. So y minus the y coordinate is equal to m x minus the x coordinate. And then there you go. That's the thing that you box. Maybe I can just use this. I should get used to that. All right. So that's pretty straightforward, I think. All right. Next, we have 4 problems that just are practicing this implicit differentiation kind of thing. Okay, so and when you get used to it, this really is a very formulaic process that you just do. So you can just sort of do it without thinking so much once you're really comfortable with derivatives. So you should remember derivative of tangent is secant squared. And then you should remember chain rule. So remember, like the fact that this has y in it means we should have a y prime somewhere. And so then like we were taking the derivative, we followed up with the chain rule because y is not x. So derivative of y with respect to x is this thing, y prime. And that's the derivative of the left-hand side. Now the right-hand side, we use power rule. We use power rule. So we get 3 over 10 x squared. Okay. So now what we've done is we've taken the implicit derivative of this whole equation. Okay. In a way, you could just like, I could label it as saying like, oh, I did this. This is the derivative that I took to go from this equation to this equation. Okay, and now, well, we need to solve for y prime. So in this case, it's very easy. Just divide the secant squared over. I guess I'll ask you this. Like, what do you get when you divide secant squared over? Because you don't need to write it as divided by secant squared. So does everyone? Okay. So what I'm asking is
it just cosine? You multiply by cosine?
That's right. Yes. I'm checking that you remember the reciprocal of secant is cosine. So yeah, we can rephrase it as a cosine squared of y when we divide it over. And I mean that just looks better, right? You don't need the secant in the denominator. Just bring it to the top. Okay, there we go. And so now we can box it. Let's box it. Let's shortcut. Haha. Okay. Yeah, for B. Okay, so doesn't look too bad. Derivative of the x cubed, 3x squared. Derivative of this middle term, immediately you should be thinking product rule. So you've got a x times y prime, or wait, I did it out of order. You got a y plus x times y prime, and then plus 3y squared y prime. And then for the right-hand side, you get 0. Okay. Everyone follow that? No questions? Okay. So then the next thing is we leave the terms with the y prime on the left. We bring the terms without a y prime, we bring them to the right. So in particular, these two terms don't have a y prime, so we're going to move them to the right. But then these terms do, so we leave them and we factor out the y prime at the same time. So x plus 3y squared equals, right, just subtract these over, minus 3x squared minus y. And then last step, of course, we divide over. And there we go. That's our answer. All right. So everyone's following? Okay, then C. First term, product rule. This one, just have to remember the exponential. So I guess it's just repeating that. So, okay, product rule, let's see, 2xy plus x squared y prime. Yeah. The second term, so the derivative of an exponential is that exponential. So we start off with that. But we, remember that there's a chain rule that is always around. And in this case, the chain rule contributes something, contributes to y prime. Implicit derivatives do that. Like we end up saying, what's the derivative of y? And well, it's y prime. So we do have this little piece there. And then right-hand side, well, that's just 1 coming from the x, right? So the x's derivative becomes 1, derivative of 1 becomes 0. So we can ignore that last bit. All right, and then we again move the terms that don't have y prime to the right-hand side, which is only this term. So we go ahead and do that. And so then algebra gives us this 1 minus 2xy, like that. Okay, and now we divide over. Y prime equals 1 minus 2xy. Should write that a little better. Y over x squared minus e to the y. And that's part C. Okay. All right. So, okay, so D looks a little bit more tricky because it has its chain rule is going to be a bit more involved. This chain rule is going to involve a product rule. Right? Derivative of cosine is the first thing that we do, and you should remember cosine's derivative is negative sine. Negative sine. Where did my negative go? And of course, we would copy down the xy, and then we would think take the do the chain rule, take the derivative of the inner function, the xy. That's going to be a product rule. So we will do the product rule now, and that is what we will get. Now for the right-hand side, it's going to be a 2x. Right, easy. Okay, now so now we want to mentally distribute this, and we leave only this term is going to be left over when we move things. So we'll have a minus x sine of xy times y prime is going to equal 2x. And then when I move this term involving the y over, it's going to flip the sign of the negative. So I'm going to have a plus y sine of x y. All right, and then lastly we divide. And so we get 2x plus y sine xy over minus x sine xy. Yep, and I can go ahead and box that. Okay, so any questions on number 2 or on this process? Everyone's okay with it? All right. Yeah, I don't want to like do the entire problem set like, in one day. I want to make sure.
I have a question.
Yeah.
I'm confused. Why did there become 2 different signs, y and an x sign?
y and an x sign. It's because we need to distribute. So see that like this set of parentheses, we have to distribute the negative sine xy to both terms, separating out that product before we then move the term that involves the y to the other side.
Okay, thank you.
Yeah. Okay. Yeah, no problem. Okay. Right. So now we talk about this related rates. All right. So I'll say that the topic of related rates is kind of tricky to explain the process behind doing it because it's sort of like puzzle solving. It's the way you think about it tends to be somewhat nonlinear. But for like the previous semester, I actually did like a set of videos where I went through a number of things. So you can find that linked to on the YouTube channel that I have. So you can find videos where I sort of go into it in more detail, perhaps if you think that you need like the extra practice or whatever. But so let me try to give a little summary about what's this called? Related rates. So usually the way that you go about this is you start by doing a bunch of like data gathering, and you want to come up with an equation that describes the situation that you're in for all time. So you want an equation that describes the problem, let's say, for all time. And then the thing is that with related rates, you always are talking about a system that varies with respect to time. So time is going to evolve, your system is going to evolve, and then you're kind of looking at the related rate is actually how quickly does some quantity change with respect to time for a specific moment in time. You always have to say it's like for like t equals 5 seconds or something like that. So then going from step 1 to step 2, what you do is you take a time derivative, which is a related rate. Take a time derivative. How do you spell derivative? Derivative. That doesn't look right to me. Time derivative of the equation, which is an implicit derivative, which is a ddt. So I'll say a ddt. I should try to write more legibly. Okay, and then the step 3 is just plug everything in. Plug everything in. Because at this stage, like you should have all of the data that you need to plug into that derived equation and get the quantity that you're after. And if you're ever missing anything, usually that's because there's an equation that you have to find that your system satisfies. Like sometimes what you have is a system where you've got multiple quantities, but they are related to each other in some way. And the relationship that they satisfy is actually just another equation. You find that other equation and you can kind of sub out one of the variables. So well, I guess, yeah, I guess I should probably specify, right? This, usually what you want to do is you want maybe I'll just say it. I don't really want to write that, but usually you want your variable to, or you want your equation to only be of one variable. Is that right? And well, I think you'll see that when we do one of the later problems. I think in one of the later problems there is such a situation. Specifically, I'm looking at number 7, but you know, I'm not trying to do number 7 today. But when we do number 7, you'll see like I'm going to set up an equation that will relate the two quantities, and that'll help our calculation. Otherwise, there's a way to go about it without using that other equation, but then your derivative is more bothersome to calculate with. Anyway, Okay, so I said a bunch of words, but let's see how this actually applies. So, all right, two people are walking, blah blah blah. I always try to diagram the situation. It's nice to be able to visually see like what is going on in our system. So we have people and they're walking, and then what's the distance? All right, so one person is going west, and one person is going north. Okay, and they make a triangle. So this is kind of like the easiest or the most common problem type that you see is where you're talking about a triangle. And so when you see that, I mean, I like to call these things x and y, and then the equation that's going to describe this situation. So imagine that the sides of this triangle are growing. Okay, so x is going at some particular and y is growing, and so the hypotenuse is also going to be increasing. But the equation that will describe the system overall, let's give this a name because I know we're talking about the distance between the two people. So the distance between the two people is going to be that hypotenuse, the length of the hypotenuse, which I'm going to label as z. Okay, so the equation that will describe this system in general is given by the Pythagorean theorem, x squared plus y squared equals z squared. Okay, so most common problem type that you'll see involves this equation. And then when we maybe I should read the whole thing. Person is traveling west at a rate of 3 miles per hour. So when I read that, I translate this mathematically to say x prime is equal to 3 miles per hour. And then the other guy is walking at a rate of 4 miles per hour. I translate to y prime equals 4 miles per hour. Okay, so note that for this type of problem, for related rates type problems, the prime is derivative with respect to time. It's d dt. Okay, this is an important thing to kind of keep in the back of your head. Otherwise, I know that lecturers, they typically, instead of saying x prime and y prime, they say dx dt and dy dt, and they write all that out. But that's just a lot of extra writing, in my opinion. Okay. Whereas like here, I can just use prime so long as I remember that prime means derivative with respect to time. Okay. All right. And then lastly, let's see, at what rate changing 1 hour after they start walking. So what the problem wants us to do is it wants us to find okay, I'll write it in full, dz dt, okay, when t is equal to 1 hour. Okay. Right. So, well, first let's draw the situation at time t equals 1 hour. So, I use this terminology of like a moving picture versus a static picture. Or a moving or dynamic picture. So in this case, what I've drawn here is dynamic because x, y, and z are variables and they're actually increasing quantities. But the static picture that we're interested in is when t is actually 1 hour. What is the configuration there? Well, it's going to look very similar, but we will know, well, given by the how quickly x and y are moving, we know that person x is going to be 3 miles from where they started, person y will be 4 miles. And then you should be comfortable enough with this set of numbers, right? 3 squared plus 4 squared equals 5 squared. 3, 4, 5 is your typical Pythagorean triangle. Okay, so we have that. And this is actually some of the data that we'll need. So now what do? Now we take a time derivative. Now we take that implicit derivative with respect to time. Okay, and so this equation is going to turn into 2x x prime plus 2y y prime equals 2z z prime. Okay, and certainly we should just cancel those twos because they're just really unnecessary there. Okay, so now we have a formula involving x prime, y prime, z prime. We want to find z prime, and we're given everything else. X, y, z, x prime, y prime. So we just plug everything in and we'll have z prime. All right, so let's see. That's going to be 3 times 3 plus 4 times 4 equals 5 times the z prime. All right, so now we solve for z prime. 3 squared, 4 squared, that should be 25, right? So 25 divided by 5, which is going to give me 5. And then, of course, we should put units because this problem has units. So this will be in terms of miles per hour. And we can box that. Okay. So you can see like my way of explanation was a bit non-linear, but hopefully you guys followed like how I was doing it. Right. So yeah, number 4 is very similar. I'm trying to decide, should I also try to do number 5 or not? I think it's better if we do 5 for tomorrow or for Thursday. All right, so 4, we've got a ladder leaning against a wall. Okay, so let's draw the situation there. Looks something like that. And we know it's a 13-foot ladder. Okay. And the top is going to slip down the wall at a particular rate. And well, if the top's going to slip, then this end is also going to slip in some way. So notice we have a triangle. Okay, well, I'm going to call this guy X, call this guy Y. And in this situation, notice that this is a ladder. We were kind of assuming that the ladder's length is fixed. So the hypotenuse in this situation does not change. And so we end up with the equation x squared plus y squared is equal to 13. And then I would immediately take the time derivative, ddt, and that's going to end up being 2x x prime plus 2y y prime equals 0. So there's a slight difference between this problem and the previous. And of course you would cancel the twos. Okay, now let's translate the rest of what the problem is saying. The top is going to slip down the wall at a rate of 1.25 feet per second. So that means y prime is equal to, and now this is something that I want to really emphasize. Notice if y is, if it's slipping down, y is actually decreasing. It's a decreasing quantity. So that means that the derivative should be a negative thing. One common mistake that I see is that people will just copy this number down and not think about the fact that it's actually supposed to be decreasing, which means that the derivative needs to be negative of it. So negative 1.25. And to make calculation easier, let's write that as a fraction. So that's negative 5/4 feet per second. Okay. How fast will the bottom be moving when the top is 12 feet above the ground? Oh, okay. So top is above 12 is 12 feet above the ground. That's the thing that will tell us the static picture. We want to find what? Moving away, how fast is the bottom? So we want to find dx dt. So I'll write that in full, dx dt. For the picture, and let's draw the configuration. So 13, the top is 12 feet above the ground, so it will be like that. And then this is actually the other common Pythagorean triple. So if you have it memorized, then you just know 5, 12, 13 is a Pythagorean triple. If you don't know that, you would have to do 13 squared minus 12 squared square root to figure out this side length, which is going to be the square root of 169 minus 144. And if you subtract that, you get square root of 25, which equals 5. Okay. But yeah, so, but this is a common triple. So, you know, some people might have it memorized, other people might need to calculate it, but you're going to get 5. Okay. What are we doing? I think now we're plugging into this equation. Yeah. Okay, so we have x, we have y and y prime. Okay, yeah, so we do just plug in. So 5 times x prime plus, and then y here is 12 times y prime, which is negative. Maybe I'll put that in parentheses. Negative 5/4 equals 0. Okay. And so x prime is going to equal, let me I'm trying to like do a lot of this mentally. So -12, and then I bring it over. So 12 divided by 5. Let me just check. Wait, no, not shouldn't be 12. It should be 3 times 5 divided by 5. It should be 15 divided by 5. Which equals 3. And then the units for this are going to be feet per second, just by reading the problem. Very good. And I'll say another thing that you can do is you can kind of sanity check your answer. You can check that it should be increasing. So in this moving picture, you expect that your x prime, your dx dt, the rate of change of x, you expect that to be an increasing quantity. I think if you if you didn't have that y prime is negative here, your results, your end result would actually have a negative. Like you would end up with x prime equals negative something, and then that would mean that the quantity x would be decreasing, and then that should give you alarm bells. Like that should immediately tip you off that something is wrong with the calculation, and you'd eventually, hopefully, figure out that what you did is you plugged in the wrong value for y prime. So here, though, everything worked out nicely because I anticipated, and we get this, and the quantity makes sense. Okay. So that's pretty much all I want to go over for today. So are there any questions before we stop? No questions? Okay, well, then let's end.